Well, thank you, Chelak, and good afternoon, everyone. So today I'm going to speak about the testing and consolidation of test samples fabricated with superworkable concrete or fiber-reinforced superworkable concrete. This work was done in Canada, was a student who was working at the time on it, finished his PhD, is Mr. Fadil Qasimi, who was working in Canada for military college, and was supported by the industrial chair on high-performance flowable concrete with adapted rheology, with contribution from private and public sector and the federal government in Canada. So I acknowledge their support for this work. So both speakers before me have been talking about this new class of high-performance concrete with adapted rheology that we are calling superworkable concrete, and the name has changed over the years. But it is this sweet zone between high-flow concrete and SCC inconsistency, where the concrete is highly flowable, and depending on the placement conditions and energy and reinforcing density and shape of the formwork, it might require some consolidation to ensure full development of mechanical properties and density, or it might not. In our industrial chair, we worked quite a bit on developing this, and then very close to our campus in Sherbrooke at the time, there was a highway being constructed by the DOT, who was a partner, and decided to use this superworkable concrete to construct some bridge elements. And you can see over here some piers of the bridges. These are the specified properties, so it's 5,000 PSI, air entrainment. These are the air contents after pumping, and the slump flow range is 20 plus or minus 2 inches, and adequate spacing factor and low RCPT. The concrete properties were measured using the slump flow, and there you see that measuring the T40 or 40 centimeter or T20 inches. And then we're using the modified slump flow that I'll talk about a little bit later, that uses, instead of 16 bars, it uses in this case 8 bars. So these concretes were cast from the top and consolidated very lightly. And we also measured the form pressure, and you can see the form pressure is much lower than the full hydrostatic pressure. Despite the very high casting rate, about 30 feet per hour, the form pressure was much less than anticipated. So there are many advantages of using superworkable concrete. In this case, the concrete that was designed met all the mechanical properties and durability requirements. It was more cost effective than SCC, but providing that the rebar density allows it and the access to consolidation allows it, which is not always the case, as you know. Because of the internal consolidation, excellent surface quality was achieved, low pressure. Consolidation energy was, compared to conventional vibrated concrete, high-performance concrete, was about 50%. And this type of concrete, given other studies, proved to be very robust. So in addition to superworkable concrete that can be used in transportation infrastructure or building applications, we were also interested in fiber-reinforced SCC for rehabilitation, or even fiber-reinforced superworkable concrete for rehabilitation or construction of the infrastructure. And there are different types of fibers that we wanted to evaluate. So the question became, when you are using fibers, what are the modifications, if any, to the workability test method that we use for SCC? And if you add a lot of fibers or the fiber aspect ratio is high enough that you don't have SCC consistency, you are in the SWC consistency, are there any modifications that are needed? So there are 3 questions really that are addressed in this presentation. The first one, what are the modifications of workability test methods? And here I'm presenting a typical mixed design for an SCC and a typical mixed design of an SCC with 0.5% fibers. These are short fibers, 1.5 inches, 38 millimeter. And you can see in the mixed design, mixture proportion, and the only thing that has changed really is the sand to aggregate ratio and the crushed coarse aggregate content. Otherwise, the mix, the binder and water binder is the same. In repair applications, we're interested in repairing piers or repairing beams or girders where there's some corrosion and the concrete is removed. And then the beam is basically repaired from the top surface, and the tension zone over here is filled with SCC. And in this case, we'd like it to be a fiber reinforced SCC to reduce cracking and restrain shrinkage and improve flexural performance. And we've done a lot of work on this, and I'm not showing this, but this is just an example of one of the fibers. And this is the conventional concrete, monolithic versus the ones with fibers. Okay, so these are the test methods that we're all familiar with to evaluate workability of SCC. And if you look at the slump and how the slump flow varies with the aspect ratio and the fiber volume, which is what we call the fiber factor, we could see that as we increase the fiber factor, we get a reduction of fluidity as expected. And there are two relationships: synthetic fibers, because they can flow easily, and they can achieve higher flow than metallic fibers. But when it comes to passing ability, Joe showed the U box, but you have the L box, you have the J ring. With fibers, there's a lot of issues, and we felt that the test is really not very adapted to using fibers. So we tried to increase the gap between the rebars to about 2.5 the lengths of the fibers, and that gave us, depending on the fiber lengths, instead of 16 bars, we had 8 bars, or in some cases 6 bars. And you can measure the diameter, and again you see that there's a separate relationship with synthetic and metallic. But we can also measure this ratio, which is the diameter divided by the height, the mean height in the middle. And that can regroup really all the fibers, whether they're synthetic or hybrid fibers or metallic fibers. So we call that a D/A. And the mixtures that you see over here highlighted, those are the mixtures where the fiber content was so high or the fiber length was so high that we got super workable concrete. So fiber reinforced super workable concrete, and we were not in the SCC consistency. And in terms of the L box, you can still use the L box, but instead of using 2 or 3 rebars, when you are using super workable concrete or fiber reinforced super workable, we recommend using only 1 rebar and doing the test. And if it does not really spread all the way, to give you the blocking ratio, you can insert a pencil vibrator and evaluate that and document how long the pencil vibrator was in that vertical compartment. So you have the L box, again, metallic fibers, synthetic fibers, and these are the super workable consistencies. And for stability, the test we like to use, in addition to the segregation test, the surface settlements, upper level we'd like to shoot for is 0.5% surface settlement. And you can see that the SCCs and the fiber reinforced SCCs and fiber reinforced super workable concretes, all of them behaved very well. So these are some typical characteristics. First one here is the fiber reinforced super workable concrete versus fiber reinforced SCC. So the slump flow obviously is lower than the SCC. The diameter over the height is below 12 versus above 12, all the way to 23. The blocking ratio, 0.2 to 0.6 versus 0.6 to 1. And the surface settlement, we also showed that is really not effective. But as Joe showed, when you have super workable concrete, where you don't have either very highly viscous concrete or not flowable enough, in this case, if you have a lot of fibers or high fiber lengths, if you do not vibrate, you start having a reduction in strength. And that is because you do not have self-consolidation. So the mixtures over here, whether they're synthetic fibers or metallic fibers, we've done splitting tensile, we've done compressive strengths, flexural strengths, they all point out to the same trend. When you reach a certain loading of fibers, you don't have self-consolidating and you need to apply some consolidation. So the question becomes, well, how much consolidation is enough? And is consolidation related to rheology? So we took here a typical SWC mixture. You can see that 400 kg per cubic meter of binder was 25% fly ash, relatively moderate water to binder ratio. And we changed the superplasticizer and the VMA, and in some cases silica fume, mainly to change the slump flow in the super workable consistency levels, so 500 plus or minus 100 millimeter. And then we measured the T40s that were between 2.5 and 7.5 seconds. And then we measured using coaxial rheometer, yield stress and plastic viscosity. And you can see again, the plastic viscosity is very similar to that of SCC, but the yield stress, depending on the slump flow, can be much higher than SCC. And as expected, you can establish a relationship between the yield stress and the slump flow. And this is all super workable concrete, and a good relationship between T40 and plastic viscosity. So to Joe Dasco's point, we can use the T40 and the slump flow to evaluate rheological properties of our super workable concrete. And then what we did is we wanted to relate the compressive strengths that we are obtaining to the consolidation energy. So we calculated the vibration energy as the frequency of the vibrator. This is a table vibrator, multiplied by the amplitude, multiplied by the time. So the only thing that we change here is how many seconds those 4x8 cylinders were vibrated on the vibrating table. And after different seconds, we calculated the energy. We measured the compressive strengths, multiple points. And if the sample is not vibrated, you get, for example, 34 megapascal. And as you vibrate, the sample achieves higher compressive strengths. And if you keep vibrating, the rate of return reduces. But this is really what we call workability energy index, very important energy to consolidate and increase strengths, basically to densify the matrix. And the other one is a compaction densification index, is really to improve surface quality. And here we are trying to correlate many different mixtures, the workability energy index to yield stress. And you can see that it's very much related to yield stress and not so much related to plastic viscosity. There's a trend, but it's a weak trend. It's really dependent on the yield stress. The higher yield stress, the higher the energy that you need, i.e. you have to consolidate the concrete more to achieve self-consolidation. But you can also, here on the right side, you can see that there's a good relationship between the slump flow, and again, it goes from about 400 to 600 when you reach this workability energy index. So when you reach SCC consistency, you don't need consolidation, or if you need it, you need very little consolidation. But as you relax it down to 20 inches, 18 inches, you definitely need that consolidation to achieve the mechanical properties. And then in terms of the consolidation densification index, which is the last part that contributes to strength gain, we see that it's also dependent very much on yield stress and not so much dependent on plastic viscosity. So we decided to put all the data on a yield stress versus plastic viscosity curve. And this is the SCC. And what is shown in blue over here, it really reflects this consolidation densification index, which is the energy that is calculated during that part of the consolidation. Very little energy is needed for SCC. But then if you make your concrete super workable, you reduce the slump flow, you need medium consolidation, reduce it further, you need high consolidation, you reduce it even further, reaching the lower end of the super workable concrete, you need very high consolidation. So you could look at your yield stress versus plastic viscosity, and what you have inside is the amount of energy that is needed to consolidate the concrete. And you can see that there are four regions. 3 of them are for the super workable concrete versus the SCC. And finally, for practical purposes, we wanted to know, well, when you are making samples, what kind of consolidation requirement you need to make test samples. So we took some super workable concrete and we prepared them using synthetic fibers and steel fibers. And then we change the fluidity. So for each of them, we have multiple mixtures. So we tested super workable concrete with 2 levels of slump flow. So on the lower end of the super workable concrete and on the higher end, and then with and without VMA for stability purposes. And then we prepared our samples. These are 4x8 samples without any rodding. So 1 lift without any internal rodding versus 5, 10, 15, and 20. And then we even took some samples and put them on the vibrating table and subjected them either to 20 or 25 seconds on vibrating table and evaluated the mechanical properties. So we did that for super workable concrete and super workable concrete with fibers, both synthetic and steel fibers. Now, we also tested the unit weight and air volume, slump, gearing, rheometer, L-box, all of these test methods. We filled the containers using 1 layer, and we subjected the containers to 10 strikes using the rod that typically is used for the slump test. So 10 internal vibration. And then when we came to the cylinders for compressive splitting tensile strengths, we used smaller rods, 10 millimeter rods that are used for 4x8. And again, different amount of strikes versus vibrating table. So I'm showing here only the splitting tensile strengths at 7 days. And this is splitting tensile strengths of the cylinders without any internal striking versus 5, 10, 15, and 20 strikes. And you can see that the splitting tensile strength is really not changing much. And these are for 4 different fiber reinforced super workable mixtures. And we also had 4 super workable concrete mixture, but in this case was VMA. And then we have the ones with VMA, in this case, over the vibrating table for 20 seconds. And you can see that there's an increase of 15 to 20% of splitting tensile strengths with the vibration. And especially when you have VMA, you have an increase in vibration, in splitting tensile strengths. But vibration or overstriking might also lead to segregation. So we cut our specimens open after every cycle of striking or at the end of vibration. And we looked at 2 indices. The first one is segregation. So we evaluated segregation coefficient. I'll show an example of that. But we also evaluated the front, the thickness of the front, where we do not have any more coarse aggregate. I wanted that to be limited to 3 millimeter. In this case, we have a high slump flow. So this is 23 inches, 24 inches, 550 slump flow with 25 seconds over vibrating table. You can see there's a lot of segregation. So here's an example of this 3 mixtures. The first one I just showed that has segregation is the one that is in blue. And here we're evaluating the density of the coarse aggregate. You can see that there's about 15% coarse aggregate at the top versus about 34%, 41% coarse aggregate at the bottom. So the segregation coefficient basically is the amount of coarse aggregate at the bottom minus the top divided by the mean. And then we also looked at the segregation front as I presented earlier. So this is one concrete that segregated a lot, and the same concrete with the same slump flow. If you use 25 seconds of vibration, but using VMA, you bring it back to basically a straight line, the same as using only 15 strikes. So in terms of segregation coefficient, super workable concrete, you can see that there's very limited effect of the striking with a small rod on segregation, and then a lot more segregation if you subject the concrete to vibration. But that number is also for the super workable concrete was, in this case, with fibers, that number increases, but then it can be reduced when you are using VMAs. So in terms of mechanical properties, we saw that the vibration is advantageous, but we could see that if the concrete is not stable, then vibrating the concrete is not a good idea because you could get into some segregation issues. And the segregation front, which is another index of evaluating segregation. Again, we see over here that the striking did not really influence the segregations. 20 seconds was fine, but if you go 25 seconds, a lot of vibration energy, unless your mixture is very stable, you're going to have issues with segregation. And finally, we looked at surface quality, looking at the honeycombs. So using surface image analysis, determining the amount of bug holes divided by the surface. This is 1.1%. And you could see that 4x8 samples without any striking, just filling them one layer will have a lot of bug holes. And those amount of bug holes are decreasing regardless of the mixture with the striking of the surface of the concrete samples, and then even more reduced with the vibration. So in conclusion, really the takeaway from this presentation is that we can use a modified gearing, whether it's 6 bars or 8 bars, to evaluate the passing ability of super workable concrete or fiber reinforced super workable concrete. In terms of super workable concrete, we recommend using 8 bars. In terms of the FR super workable concrete, depending on the length of the fibers, you need to have 6 or 8 bars. We try to keep 2.5 lengths of the fiber as spacing. The consolidation energy that is needed to consolidate and increase mechanical properties and density of super workable concrete and fiber reinforced super workable concrete is mainly dependent on yield stress or slump flow. When preparing samples to determine slump flow, gearing, air volume, we recommend casting the super workable concrete in one layer and striking it internally using 10 strikes using the rodding. And when we are preparing mechanical property samples for mechanical properties, we recommend also casting them in one lift and then striking them 20 times. Vibration can work, so you can vibrate it, but it's risky. If your concrete is not stable, and especially if it's fiber reinforced concrete with metallic fibers, you can have issues with segregation. So this is what basically the last presentation. So thank you very much, and I'll be happy to have any questions.
Thank you, Kamal.